Okay, this is my project on projectiles. So the problem we're given is that John kicks a ball with an initial velocity of 14.5 meters per second at 20 degrees above the horizontal. He kicks his second one, which has a hang time of 2 seconds. What is the initial velocity and launch angle of the second ball if it travels the same distance as the first ball? So what we're going to do to solve this problem is we're going to split it up into multiple parts. So for the first part, we have that the first ball is kicked at 14.5 meters per second at 20 degrees above the horizontal. So John kicks the ball with an initial velocity of 14.5 meters per second at 20 degrees. And for this first part, we're going to be solving for displacement. Okay, what we're going to do first is we're going to split this up into its horizontal and vertical components. And we're going to fill in what we know without having to do any math. So we know that the vertical displacement is 0 meters since the ball is kicked from the ground and lands right back on the ground. We also know that the horizontal acceleration is 0 meters per second squared because there is no force acting on the ball horizontally once it is kicked. We also know that the vertical acceleration is negative 9.8 meters per second squared since once the ball is kicked it is in free fall. Now we're going to make this into a right triangle. So that gives us the initial velocity with 14.5 meters per second, which is the hypotenuse. We are given that the launch angle is 20 degrees, and we're going to be solving for the opposite and adjacent sides to find the horizontal and vertical initial velocities. Okay, so to solve for the opposite side length, we're going to use SOHCAHTOA, and more specifically, we're going to use that the sine of x, the sine of the angle, is equal to the opposite side length over the hypotenuse. Now we're going to manipulate that to solve for the opposite side length. So we have that the opposite is equal to the hypotenuse multiplied by the sine of the angle. And in this equation, we have that 14.5 multiplied by the sine of 20 gives us the opposite side length. So the opposite side length is 4.96 meters per second, which is our vertical initial velocity. And when we are solving for the adjacent side length, we are given that the cosine of the angle is equal to the adjacent side over the hypotenuse. And when we manipulate that to solve for the adjacent side, we have that the adjacent side is equal to the hypotenuse multiplied by the cosine of the angle. So in this equation, we have 14.5 multiplied by the cosine of 20 gives us the adjacent, which is 13.63 meters per second, which is our horizontal initial velocity. So when we fill in the chart based on the work we did from the last work, we have that the initial velocity of the horizontal component is 13.63 meters per second, and the initial velocity for the vertical component is 4.96 meters per second. So horizontally, the velocity will not change, so the final velocity is 13.63 meters per second. This is because of the acceleration being 0 meters per second squared. So the velocity won't change. And vertically, the initial velocity is 4.96 meters per second, and the final velocity will just be the opposite of that since the launch angle and the angle at which the ball hits the ground are both equivalent. So the final velocity will just be the opposite of the initial velocity for the vertical component. So in order to solve for time here, we're going to need the acceleration equation, which is the final velocity minus the initial velocity all over time. So we're going to solve for time, so that we're going to make that final velocity minus the initial velocity over acceleration. So we have time equals the final velocity, which is negative 4.96 meters per second, minus the initial velocity, which is 4.96 meters per second. So that gives us negative 9.92 meters per second, and we have to divide that by acceleration. So negative 9.92 divided by negative 9.8 gives us 1.01. Meters will cancel here, and seconds squared divided by seconds just gives us seconds. So the time here is 1.01 seconds. So when we fill in our chart, we now have that the time is 1.01 seconds, and that will be the same on both sides. So when we are going to be solving for the horizontal displacement, we have the displacement equation, which is the initial velocity times time plus zero point 0.5 acceleration times time squared. And since acceleration is 0 in the horizontal component, um, this is just going to cancel. So you're left with the displacement equals initial velocity times time. So now we have that the displacement equals 13.63 meters per second times 1.01 seconds. So seconds here will cancel. So now you're left with 13.77 meters when you multiply 13.63 times 1.01. And this will be the displacement that the first ball travels. So this is going to be our second part of this equation where we focus on the second ball. So we have that John kicks the ball, and we know that the total hang time is 2 seconds. And from our first step, we know that the displacement that it travels is 13.77 meters. And in this part, we're going to be focusing on solving for the initial velocity and the launch angle. So for this second part, we're going to have a new chart splitting up the horizontal and vertical components. So from the previous part, we know that the horizontal displacement is 13.77 meters. And we also know that the vertical displacement is 0 meters since the ball is kicked from the ground and lands on the ground. We know that the horizontal acceleration is 0 meters per second squared because there is no force acting on the horizontal component once it is kicked. And we also know that the vertical acceleration is negative 9.8 meters per second squared because once the ball is kicked, it is in free fall. And it is given in the equation that the time is 2 seconds. So we're going to write that down for both vertical and horizontal. So first we're going to be trying to solve for the initial velocity for the horizontal component. And what we're going to do is take the displacement equation and we're going to make it so you solve for the initial velocity. And we're able to do this because the acceleration is 0, so we could just take that part out and just solve for initial velocity. So we have the initial velocity is equal to displacement over time. So we have the displacement 13.77 meters over 2 seconds, which gives us 6.89 meters per second, which will be our initial velocity for the horizontal component. So when we fill in what we know, we have that the horizontal initial velocity is 6.89 meters per second. And that also makes the final velocity for the horizontal component 6.89 meters per second since acceleration is 0, so there's no change in velocity. We're going to find the vertical initial velocity, and how we're going to do that is we're going to take the displacement equation and we're going to plug in what we know. So we have 0 meters is equal to 2 seconds multiplied by the initial velocity plus 0.5 times the acceleration, negative 9.8 meters per second squared, times time squared, so 2 seconds squared. So we're going to do unit analysis to solve this part of the equation first. So we have 1/2, which is 0.5, times the negative 9.8 meters per second squared times 2 seconds times 2 seconds, which is 2 seconds squared. So seconds will cancel. So you're left with negative 19.6 meters. So that gives us 0 meters is equal to 2 seconds times the initial velocity minus 19.6 meters. So what we're going to do is add the 19.6 meters to the other side of the equation. So we have 19.6 meters equals 2 seconds times the initial velocity. Now to solve for initial velocity, we're going to have to divide by 2 seconds, which is expressed through here. So we have 19.6 meters divided by 2 seconds, which is equal to 9.8 meters per second, which will be our initial velocity for the vertical component. So we're now going to fill in what we got from the last work into the chart. So we got that the initial velocity in the vertical component is 9.8 meters per second. and that would make the final velocity negative 9.8 meters per second, since final velocity would just be the opposite of the initial velocity. So when we make this a right triangle to solve for the total initial velocity, we have that the opposite side length is 9.8 meters per second, and the adjacent side length is 6.89 meters per second. So in order to solve for the initial velocity, which would be right here, we're going to use the Pythagorean theorem. So we're going to have the initial velocity squared, which would be c squared, is equal to 6.89 squared plus 9.8 squared. So you have that the initial velocity squared is equal to 143.52, and if you take the square root of both sides, you're left with the initial velocity being 11.98 meters per second. So in order to find the launch angle, we're going to take the inverse tangent of x. So we have the inverse tangent of 9.8 and over 6.89 would give us the angle, and that angle would be 54.91 degrees. So that leaves our final answer being John kicks the second soccer ball with an initial velocity of 11.98 meters per second and with a launch angle at 54.91 degrees. And that is the end of this problem.